coffee. The finest organic suspension ever devised. Got me through the worst of the last 3 years. I beat the board with it.
Okay, bonus episode 20. Welcome to Coffee Literature Review. I'm Chris Hendon, and I'm joined by Doran Pennington. We were supposed to have a guest today, by the way, but it's sixth season. Everyone is feeling a little unwell, so they had to back out at the last minute. We'll get that guest on next time. Today, we're discussing a paper that was published in the journal Scientific Reports, not Nature, but published by the publishing group that publishes Nature, SciRep. Title of the article is Caffeine Content in Filter Coffee Brews as a Function of Degree of Roast and Extraction Yield. The paper is out of the Department of Physics at Berry College, as well as a collaboration with the Department of Chemistry at Drexel University in Philadelphia. When you roast coffee, you lose mass. It goes out of the smokestack, out of your roaster. The more you roast the coffee, the more mass you lose. And in that mass, some fraction of it is caffeine. And the reason is you're above the sublimation temperature, so some caffeine will volatilize and become part of the lost organic material as you roast. But that doesn't mean that a dark roast coffee that you physically drink, like the brewed dark roast coffee, has less caffeine. Because you had to use more beans to get the same amount of weight, right? So as more physical beans go into brewing 10 grams of dark coffee than beans went into 10 grams of light coffee. But if each of them started with the same amount of caffeine, but now there's more beans in the dark roasted coffee, what you end up having is you have inherently a trade-off. How much did you destroy? And if that percentage of destruction is less than that added number of beans as a percentage, then you're going to see dark roast coffee has more caffeine than light roast coffee. And that's it.
But light roast coffee can have more caffeine in the cup, provided that you are able to extract it efficiently and pull out the remaining material that, otherwise would have been lost to the smokestack, like Chris said.
We're going to get into it now. You're going to see that there's nuance with natural versus washed, and it gets complicated, but just keep your eye on the prize here, that what it's about is about dry mass, not extractable mass. And that's the most important thing that's not really highlighted as clearly as it could have been in this paper. But with that in mind, let's go. All right. What is the basic question here, Doran? Does dark roasted coffee have more caffeine than light roasted coffee when you brew it the same way?
Yeah, so the way that they motivate this paper in the introduction is they say there's a lot of conflicting information in the literature about this. There are some papers that say there's no difference in the degree of roast on the ultimate caffeine content. There are some papers that say roast degree linearly corresponds to caffeine content. There are others that say it inversely corresponds to caffeine content. And they're saying that because changes in caffeine concentration tend to be pretty minor, that it takes a lot of control to actually tease out the underlying driver of caffeine content.
Right. The thing is, caffeine's produced by the plant. So you're not going to make any more caffeine as you cook something. It is possible that you could be destroying caffeine as you cook something. So in principle, one hypothesis could be that the darker the roast of a coffee, the less caffeine is available, full stop. Ignore extraction, just talking about the dry mass of the material. In principle, could be equal amounts or less, but never more. With that in mind, then coffee brewing is the process where you're adding hot water to coffee beans, trying to get some of the material to dissolve in that hot water. And one of the challenges with that is that as you roast the coffee, you're creating new compounds. So not only might you be affecting the caffeine concentration in the bean, but as you also roast darker, you should be creating new material. Perhaps some of it is more soluble, and perhaps some of it becomes less soluble. It's a problem because the composition of the coffee depends on the roast. But during coffee brewing, you're not brewing and trying to extract everything. You're just brewing for a finite amount of time, trying to extract some things. Ideally, we're trying to do it to make a cup taste good. There may be other motives as well, like perhaps you're trying to go for high extraction yields because you have an economic argument to do so. But I think the critical point here is that many scientific articles try and address this idea of equilibrium extraction. In other words, can we extract as much of that material out as possible while controlling for one variable, for example, brew temperature? And to get to equilibrium, typically you have to wait around for a long time. So brew time inherently is one of these variables in equilibrium studies where we just push it to a really long time and see what we can get out. But in real life, coffee brewing is not an equilibrium process. It is a kinetic process where you're trying to stop it at some point. With that in mind, you go back to the title of the paper. This is caffeine content in filter coffee brews. So they are specifically not trying to go to the equilibrium brew parameter space, but rather to the kinetic parameter space of brewing an AeroPress in this case between, let's say, 0 and 2 minutes. They also do a 10-minute time point. You can interpolate between those points, but I think roughly speaking, most people who brew AeroPresses are typically in that zone of what, like 1 to 2 minutes. So Doran, tell us about the experimental setup, how they roasted coffee, how they brewed it.
Yeah, so I'll first say that someone asked me this question quite a while ago about, does darker roasted coffee have more caffeine in it in the cup? And I didn't know the answer, but I was thinking about it, and the answer that I gave was, well, if you think of darker roasted coffee, the beans are going to be more porous. You're generating more CO2 in the bean. You're breaking up the cellular matrix. So I thought that extraction would be more efficient, and that if you're in this kinetically limited space, you're probably going to pull more caffeine out. So that was my guess. And it turns out that you have these competing processes where the darker that you roast something, people think of sublimating caffeine or destroying caffeine, so there's overall less. But if you make it more accessible and easier for the water to contact the coffee in more places, then it should pull out faster. And the question is, do those balance perfectly, or is it tipped in one direction or the other? So the way that they approached this paper is they tried to control basically every single variable that they could. They sourced a bunch of green coffee from Royal Coffee, which I have some personal experience with. They run a really good cafe down in San Francisco. And it's also very cheap because they are the importer. So they serve coffees that they import, and I like that place. But they imported a bunch of washed Ethiopian coffee and natural Ethiopian coffee. And they tried as best as they could to control, elevation of growing, moisture content, density, and so on. And then they systematically roasted this coffee by going to a time post first crack. So once first crack was hit, they took some coffee out at that time, and that was their time 0. Then they also had 1 minute, 3 minutes, 5 minutes, and 7 minutes post first crack.
That's actually a pretty standard data point in coffee roasting. People care about a few things depending on which school you learned roasting from, whether it was along the lines of like the Rob Hughes style of measuring mass loss, total mass loss versus time after first crack, or the development time, whatever. People do this. That's fine. Let's assume for this paper that the roasting is more or less aligned with what people do. You can see the roast curves in the paper. There's something I would report myself. I think they look fine. They're roasting on a reasonable roaster. It's the Bullet version 2. It's an electric drum roaster, and they're doing 500-gram batches. The critical thing here is I believe they roast to multiple different degrees of darkness, ranging from, I would say, objectively very light, where they stopped exactly at first crack, to going pretty far beyond first crack. So going basically 100% extra time beyond first crack. So again, to pretty dark, I'd guess. It's hard to tell because you can never really see color in these papers.
Well,
right?
some of these papers in the SI have pictures of the beans, and I was hunting through the SI looking for that, but sadly no bean pictures.
A lot of nice pictures in the SI, but not of the beans in color. Only scanning electron microscopy images, right?
Yeah, and so I think we've established pretty well in the coffee world that the way that you roast coffee affects how it grinds. And that's obviously going to play a role in the extraction process. And so they tried to control for that by taking 2 sieves and grinding coffee fairly coarse for an AeroPress, and then taking 2 sieves and only collecting what lies in between them. So they have a 700 micrometer and a 900 micrometer sieve. And so ideally they're filtering out everything bigger than 900 micrometers and smaller than 700 micrometers, but coffee particles have irregular shapes. So some of the big ones get through, some of the smaller ones might get through too and just get stuck. And so they report particle size distribution, and they seem to lie almost confusingly perfectly on top of each other.
Yeah. Earlier work in my lab and other people's work has shown that as you roast darker for the same burr aperture, in other words, same grind setting, dark roast coffees tend to produce smaller particles. The reason for that is there's a change in brittleness and change in moisture, so the coffees will inherently shift smaller. So to see sieved coffee result in almost exactly overlapping particle size distributions of the boulders is quite surprising, actually. So I that was the one data point in here that made me think maybe these coffees weren't that far apart in color, but it's hard to tell. That's really hard to tell. I mean, it's nice that they overlap because it actually separates one variable that you and I would have picked at, which is the fact that particle size shifts, then you're going to have different kinetics. We probably should talk about the porosity now, even though in the paper it shows up later. Because obviously, anyone who's ever seen a microscopy image of coffee, roasted coffee, knows that there's holes in coffee. And this has been a problem for many people over the years developing models, including myself.
Yeah, and then if you assume that the particles are spherical and they have all of these pits and holes in them, then your actual surface area that can contact water is markedly higher than just a straight sphere.
And they did the work, right, in this paper. So they're fundamentally comparing a natural versus a washed. Later on in the paper, Doran, they have one figure that compares porosity as a function of roast time. And I think they only present that for the washed coffee. There are some curious looking polynomials they fit here to try and maybe help us predict the degree of porosity as a function of roast time. What do you think of those?
Yeah, I don't think it's necessary to fit a polynomial to these if you're not trying to make some assessment of what's going on in between your data points. If you just want to look at the data points as they exist, I don't think you really need this equation because it has no physical basis. It's just kind of a least squares fit, and how do you know if that's an accurate model of your data? But what it seems to suggest is that as you roast darker, the amount of pores increases and the area of your pores increase, which makes sense, right? So the darker you roast, the more you make CO2, it wants to escape out of the bean. And you're basically making holes in the coffee. But the density of the pores when you go really dark actually decreases, which they claim is, you could think of a bunch of small pores aggregating together, because you're breaking the walls that exist in between the pores that you formed earlier that are smaller. So you're making bigger pores, but there are now less of them, so your pore density decreases.
Water has to go in these pores. That's the basic reason why people are even looking at this at all in this paper, is that if you make a bunch of pores, you'd expect then that water should be able to get to caffeine easier. And so you need to separate out the component that's coming from the fact that coffee changed morphology or porosity from the amount of caffeine that is contained within the coffee itself. They did a reasonable job of that. I actually think that's kind of not that important in this paper because at the end of the day, you don't really get to control the pore size. You have a coffee, you need to pour hot water on it. The pores are what they are. Whether or not everyone would agree with me on this, if you look at the pore distribution here as a function of roast, not as predictable as you'd like. I mean, it's not linear, let's put it that way. All sorts of crazy stuff happens. You're roasting coffee, you're heating up organic material inside a drum roast. It's not like this is going to help you all that much beyond the general point you made, which is darker roasts have typically more pores. Fine. Okay, so with that in mind, hypothesis then is, okay, perhaps as you roast darker, maybe you get less caffeine because you sublimed some of it out of the roaster or degraded it in some way. But because porosity is increasing with darker roasts, perhaps you're going to get more available caffeine for given brew times. Is that what happens?
Yeah, so getting on to the actual brewing of the filter coffee. So they make some controlled brewing water from ultra pure water and the addition of some salts. And then they rig together this insane contraption, which there's like a diagram in figure 2. It's it looks like a drill press with an AeroPress in it on top of a beaker connected to a force gauge. And so they're basically cranking on this thing to 1,000 newtons because they said at 1,100 newtons, they broke the AeroPress. So, so they dropped it back a bit.
This looks like a contraption that you would. What's that series of movies where? What is that movie? Saw.
Oh my God.
This
just connected to your mouth.
Yeah, this looks like something where it's like got your big toe underneath it and they're going to get you. The reason they did this is because they wanted to separate out the impact of pressure. And when I saw this, I was like, I know another way to separate out pressure from coffee brewing. It's where you use a process that doesn't have pressure involved.
Yeah, use a V60.
Yeah, or like a French press that works extremely well. But no, or cup it even.
Yeah.
But nonetheless, they brewed coffee and they wanted to filter out the particles, so they needed to use a filtration system, an apparatus that had paper in it, and so they used an AeroPress with filtered paper.
Yeah, and they're doing, for their brew times, they're doing 1 minute, 2 minute, and 10 minutes, which is curious. I don't think I know anyone that does a 10-minute AeroPress, but I guess the idea behind that is to approximate equilibrium.
It's to approximate someone who intended to do a 2-minute AeroPress. So, all right, and here's what happens, right? So you have a 2 minute, 1 minute, 2 minute, and 10-minute AeroPress. And we need to define one more thing. Listeners of this pod will probably know what extraction yield is, but it's really, really important to define it again. Extraction yield in this case is defined as concentration of the brewed coffee times the mass of the brewed coffee divided by the mass of the coffee dose. In other words, the amount of coffee material that's solvated divided by the dry mass that you used in the first place. This is really important because this is a metric that we use and other people use as an efficiency metric of how much material did you get out versus the total amount of material that was available in the first place. The upper limit of extraction yield is not 100%. I mean, in principle, it's 100%, but in practice, not every single thing in coffee is soluble. So,
yeah. Can you imagine taking a portafilter out of an espresso machine and there's nothing in it? It's just all gone.
You and I did that experiment that one time. We put instant coffee in an espresso portafilter.
Yeah, but we made goop.
Yeah, it was bad.
It was like, it turned into cement.
Yeah, it was a bad thing. Okay, that's not what they're doing. They're brewing coffee in an AeroPress and measuring extraction yield. Across the board, light roast coffees for the same everything else, same particle size distribution, same brew time, same brew water, everything. Light roast coffees give you higher extraction yields than dark roast coffees in this data set. And the difference is really large for naturals. So if you have a light roast natural, the extraction yield can be like up to 21% at a 10-minute brew compared to the dark roast equivalent, which can only get you about, let's say, 17.5%. So you're looking at 3.5% bonus just for going lighter with the natural. That difference is much, much less for the washed coffee. And it's still true that the light roast coffees tend to more or less be extracted to a little bit higher than the dark roast, but the difference is less. And you can relate that to the porosity thing we were talking about before, but we don't really need to go on about that. I think the critical point here is simply that there's more extractable material that's soluble in water, evidently, for naturals that are roasted light than for naturals that are roasted dark.
Yeah, and that could be due to the different distribution of porosity, but they don't present that data, unfortunately. At least not that I can see.
We didn't. It's not really as clear as I would have liked to have seen it, because they should have done the natural versus washed comparison. My guess actually is that the natural probably has they showed one microscopy image in the SI and has this massive hole in it. My guess it was pretty hard to quantify the natural, so they did the wash because it was much more regular. Let's go back one step to the hypotheses of this, though, is that as you roast darker, in principle, you're doing oxidation chemistry, and oxidation chemistry can yield more soluble stuff. But as you roast really dark, you start to carbonize material, and so that becomes less soluble in water. So there must be a critical point. You would think there's a critical point.
Yeah, if you look at this data, just stopping here, like if you don't read any further than this and you see the extraction yield super high for the lightest roast, I think your conclusion is, oh, there's more caffeine in the lighter roast.
That is what you might conclude. And I think that actually is the fundamental reason that people have been misled in this topic over the years, is that they see higher extraction yields for light roast coffees and typically would say, well, that's a more concentrated cup given the same brew parameter space, therefore must have more caffeine in it. Is that right?
Yeah, so the next figure, figure 5, shows HPLC chromatograms. So this is basically passing coffee material through a packed column and separating out the chemical components.
For the natural specifically, which is, I'm glad they picked the natural for this one.
Mm-hmm. Yeah, because the natural had the most variability.
Yeah, light roast got you the highest extraction yield by a lot. Therefore, this chromatogram tells you exactly whether it's coming from other material existing in the coffee or fluctuations in caffeine.
Yeah, and so what you see is their method is pretty short. So they're not separating out every single molecule in coffee, but they do get resolution between the major chlorogenic acids, 5 and 4-CQA, and caffeine. And what you see is that as you roast coffee darker, you deplete almost entirely the chlorogenic acids. Between 0 minutes post first crack and 7 minutes post first crack, it's like 100% to 2%. It's a massive reduction of the CGAs, but the caffeine peak is almost the same area for all of them.
Roast does not change the amount of caffeine that much.
Yeah, and if you think that you're subliming caffeine in the roaster, you would think that, okay, well, the longer I roast, the less caffeine there will be because it's going to evaporate. But what they're showing is that, you actually get more or less the same amount of caffeine out.
That is a really important piece of data for this particular study, because that tells you that if extraction yield has gone down, but caffeine content stays the same, then if you make an equally concentrated beverage, dark roast coffee will have more caffeine in it relative to light roast for the same concentration, because in order to obtain that same concentration, more of that mass fraction has to come from caffeine. So remembering that the extraction yield is the mass fraction that you solvated, if you change no other parameters besides the roast of the coffee, you tend to get a more dilute cup because the extraction yield is lower. If caffeine was not destroyed during roasting, but you're losing mass otherwise, then if I weighed out 10 grams of dark roasted coffee, more of that coffee should be caffeine. Therefore, dark roast coffee should, in principle, have more caffeine in it if it is not being destroyed by roasting. If it is being destroyed by roasting, then you can get the result that they have from the HPLC, where if you weighed out 10 grams of light roast coffee and 10 grams of dark roast coffee, and you extracted it, and you found they had the same amount of caffeine in them, but you know that the dark roast coffee lost a bunch of mass on the way to getting to that point, that means that some of the caffeine was also lost in that process. In other words, roasting is destroying some of the caffeine. It happens to destroy about the same percentage amount that is lost of total mass as caffeine mass. In other words, if I lost 10% mass, some fraction of that was going to be caffeine that's been lost, so that at the end, when you try and brew it, it looks like light roast and dark roast coffee have the same amount of caffeine.
Yeah, and then the other thing that you need to think about is if you're weighing out coffee at home, the number of beans that you dose out for a light roast coffee will be less than the number of beans that you weigh out for a dark roast.
So it's not surprising, Doran, this is complicated when people try and brew coffee, because I think the nuance that obscures both the mainstream media when they write an article about this, but also obscures the barista when they're trying to brew coffee and make an assessment of bitterness to sort of extrapolate to caffeine concentration, is there are a lot of different very important but small steps that you have to take to appreciate that light roast coffee beans have more caffeine in them than dark roast coffee beans. But you have to use more beans in dark roast brews to get the same amount of coffee mass into that brewing system. Of that mass fraction, there's still the same amount of caffeine in that cup, whether it was light or dark. And so as a result, if you look at the amount of caffeine that makes up the soluble material coming from light roast coffee, it is proportionally less caffeine because there's a lot more other stuff there too. But the amount of caffeine in the light and the dark is the same. So you might then conclude that dark roast coffee has more caffeine per soluble material. But that's not the right way to think about this.
You can see that for the brews that approximate the kinetically limited regime where, you're not pulling everything out of the coffee, you're not doing a 10-minute AeroPress.
Yeah, 1 to 2 minutes.
It's
say.
A bit fuzzy. Like there's not a super clear trend about, especially in the washed coffee.
The washed coffee is very difficult to predict.
Yeah, it's not like you can say, if I roast darker, I get more caffeine or less caffeine. It kind of jumps around.
So for me, I would have actually plotted this the other way. I would have plotted brew time versus extraction yield and had some way to show the caffeine content as the marker. You see what I'm getting at?
Mm-hmm.
And why I'm making a point about this is because if all you do is turn to figure 6, and we'll post a photo of figure 6 on Instagram, what you'll see is that if you take a light roast coffee, you'll tend to have higher extraction yields than the darker roasted coffees. And if you brew it for longer, you tend to have higher extraction yields. And if you brew it for longer, independent of whether it's light or dark, you get more stuff out. And so the longer you brew, the more caffeine ends up in the cup. But if you compare light to dark for the same brew time, the amount of caffeine that ends up in the cup it's pretty, I mean, we're in plus or minus 5 milligrams total here. This is basically unchanged.
Yeah, and then if you try and simplify it for yourself and say, all right, I'm only going to look at the 1 minute brew for the washed coffee, varying with roast level, you see that the lowest caffeine content is for the lightest roast, but the next lowest caffeine content, so like just slightly more than the very light coffee, is one of the intermediate roasts, the 3 minute roast. And then it goes to 7, and then it goes to 5,
and then
it goes to 1.
And they're all plus or minus like 5 milligrams.
Yeah, and they have error bars on here that look fairly convincing, but I think the takeaway is it's extremely hard to predict, which is kind of probably why there's so much disagreement in the literature and why there's not a consensus about this.
Executive summary here, Doran. Summarize what happened to chlorogenic acid.
Yeah, if you roast it, it goes away.
Okay.
It's gone.
Yeah, it's gone. And it turns out it's gone so much that even if you push extraction yields up, you don't actually see more chlorogenic acid really, because chlorogenic acid is seemingly soluble pretty rapidly.
Yeah, the only traces that seem to have an increasing amount of chlorogenic acid with increasing extraction yield and brew time are the really light roast coffees.
And makes sense.
Yeah.
Because they're the ones that have a lot of it. So
yeah, so then you're limited. You
Yeah.
know, then there's some mass transport limitation when you're trying to pull it out of the coffee.
yeah. Let us get to the question. Does a light roast coffee and a dark roast coffee brewed exactly the same way, do they have different caffeine concentrations?
Perhaps.
Yeah.
Who knows?
Yeah, who knows?